about today was, eigenvalues and eigenvectors. And as we notice here, there is a, that for a given matrix, there can be, there can be vectors and integer pairs, vectors and scalar pairs, such that the matrix times the vector gives you the same thing as the scalar times the vector. And so this pair of scalar and vector, okay, have to kind of encode a lot of information about the matrix. That's kind of, I guess, the story here. So how do we compute these scalars? Are called eigenvalues, okay? And again, when you took a linear algebra course, you went through this a little bit. How do you find it? Find what it turns out that any matrix, if you have a matrix of rank n, meaning that it is, all the rows are linearly independent, and that it's kind of a well-formed matrix, okay, it will have n distinct eigenvalues. And these can be found by by basically factoring a matrix. That if you take an equation, what they call the characteristic equation of a matrix, if you take the matrix and subtract from it lambda, which is supposed to represent the eigenvalue, times the identity matrix, you get a matrix that looks, a matrix where there's going to be these lambda terms on the main diagonal of the matrix. The determinant of that matrix is a polynomial, okay? It basically, if you remember how you evaluate a determinant, it's sort of one term times the other term times the other plus, and it's a sum of these things. The determinant, it will give you a polynomial. When you factor that polynomial, all the roots of that are going to be eigenvalues, okay? So you can sometimes have repeated eigenvalues. Here, -1 is going to be twice an eigenvalue of the matrix. 2 is going to be an eigenvalue. But basically, by doing linear algebra things, you can compute what these eigenvalues are, okay? And these eigenvalue eigenvector pairs have some very interesting properties that are kind of important to us. One is, as I said, if you have a full rank matrix, you've got n of them. If you have an n by n matrix, you have n eigenvalue eigenvector pairs. Okay. A second property that's kind of important of these eigenvectors is that they are all mutually orthogonal. Okay, so if we think about, let's say, like when we have axes, vectors that define axes in 3 dimensions, typically we are looking at like vectors 1, 0, 0, 0, 1, 0, 0, 0, 1. These matrix vectors are kind of orthogonal because the dot product of them is 0. Okay, and that's kind of saying that basically the axes are the things that we use as axes in Euclidean space or something like that. The dimensions are orthogonal, are kind of independent of each other. Okay, now it turns out that for every pair of eigenvectors, okay, their dot product is 0, and so all vectors are equally or kind of orthogonal. And so we can kind of think of the eigenvectors as kind of being a set of axes, okay, in an n-dimensional space, okay, and that has an interesting implication sometimes, okay. So those are the properties that we care about, and these vectors and values can be solved basically by solving found by solving these linear systems of equations. I showed before how you would compute a eigen value for every eigenvalue there is associated with it a given, a particular eigenvector. Okay, how do we find what that vector is? Well, we know that the main definite equation, the property of an eigenvalue eigenvector pair, is that the matrix times the vector is the same as the eigenvalue times the vector. And so by factoring this thing out, in general, we know the original matrix. If we want to know what the eigenvalue is, we know this. Our goal is to find the resulting vector. Well, this basically reduces to solving a system of equations, okay? Because we know that what we really want for our vector is that this times this plus this times this has got to be equal to 0, okay? Times this, okay, this times this plus this times this has got to be equal to 0, and this times this plus this times this has to be equal to 0. Solving a system of equations like that gives us the vector associated with the eigenvalue. So we know that we have ways of doing it. We also have ways of doing this faster for important eigenvalues. Okay, so if we look, another way to interpret this equation, if we say it's this vector, that the matrix times the vector is equal to the eigenvalue times the vector. By dividing both sides by the scalar eigenvalue, we get an equation that looks like this. The vector should be equal to A times the vector divided by L. If you guess at what the vector is at first, you could use this equation to give you an updated estimate for what the vector is. And after a certain number of iterations, it should hopefully converge on a vector such that v is going to be the same on both sides of the equation. And that gives you the eigenvector associated with that eigenvalue. Any questions about that? Okay. This should be review of linear algebra that you had. And I remember the eigenvector, eigenvalues part as being relatively painful. But I think now we have a basic view of it. The reason why, one for us as, let's say, data scientists, the reason why eigenvalues are going to be very interesting, the eigenvalues and vectors, is that we can represent matrices in terms of these eigenvectors, okay, and eigenvalues, okay? In fact, any matrix, okay, M, if we have an n by n symmetric matrix, okay, we can decompose it into the sum of n eigenvalue eigenvector products. When we have a vector, an n by one vector, and we multiply it by its transpose is going to be a 1 by n matrix vector. And this times this is going to give you an n by n matrix, where we're going to weight the elements in here based on this eigenvector, eigenvalue lambda. The fact that we can decompose any symmetric matrix into this is very interesting, because the matrix itself is going to be the sum of these n products. But how important each one of these terms is for the matrix is kind of summed up by the this eigenvalue. Okay, so we can actually approximate the matrix by only taking the terms with the leading eigenvalues. Okay, and this is going to give us a way to take a data matrix and approximate it by a smaller feature vector. Okay, sort of like when we were talking about matrix factorization. So remember, eigenvalue decomposition works on symmetric matrices. We talked about it has to be an n by n symmetric matrix. The covariance matrix, okay, which was, remember, A times A transpose, okay, for any matrix, kind of measured, again, the similarity of rows of the original matrix. That was a symmetric matrix because the similarity of row ij is the same as the similarity of row ji. Because it is symmetric, you can do a kind of a dimension reduction on this matrix, okay, by just taking the most important terms. Now, if we remember the covariance matrix of the Lincoln Memorial, it looked sort of like this. Remember that there were kind of the steps here and the columns here, and I guess the roof over here, okay? And what this is now showing us is what is the error, okay, when we try to reconstruct the matrix based using one, just a leading eigenvector, the 5 leading eigenvectors, and the 50 leading eigenvectors. And what you're seeing here is that as you add more and more vectors to your representation, okay, you're gradually reducing the amount of error in our ability to reconstruct the covariance matrix, okay? But using a relatively small number of dimensions gives us a relatively good approximation of the matrix, okay? And this is an important thing to be able to do. In general, we would like to be able to take complicated big matrices and compress them into smaller vectors, okay? That would, smaller matrices that will encode as much of the information as possible. If we were given a symmetric feature matrix, okay, this kind of eigenvector decomposition is a good way to deal with that. Any questions about this and how we deal with the eigenvector decomposition? Why it's an important idea? Why, unfortunately, right now we're still limited to dealing with symmetric matrices? Any questions? This is why why we get very, very interested in a related technique called singular value decomposition, or SVD, okay? Basically, for any n by m matrix, regardless of whether it is symmetric, okay, it will have a factorization as follows, okay? There will be this is supposed to be at the end. This dimension has to be n. The last dimension has to be m, okay? This is going to produce a, I believe an n by n times n by, this matrix, I believe, is going to be n by n. This matrix is going to be n by m, and this is going to be m by m, okay? The result here is that we can factor our matrix into basically these terms, with these pairs, where with the eigenvector decomposition, we had one vector v and we had v transpose. And that was what we multiplied to get a big matrix. Here, the U matrix is different than the V matrix, but still we get a factorization where the center term D is going to be an identity matrix where each term is weighted, on the main diagonal is weighted. So we're going to get an idea for every row column pair how important it is. And maintaining only the important rows and columns enables us to compress the original matrix, okay, with a smaller number of features, okay, such that we can represent a lot of the matrix. Any questions why we want this? Okay. Again, the reconstruction of this, well, is basically like I said, okay, before, that when you well, okay, that basically that when you've got two vectors, the outer product, the inner product is kind of the dot product it produced if you had an n by 1 matrix and a 1 by m matrix. The inner product just basically was like a dot product and gave you one number. The outer product gave you an n by n matrix. Okay, and basically any product of matrices can be expressed as the sum of the outer products, okay, of what we get from the SVD, okay, and that's kind of just basically restating what I have here. The interesting thing is to kind of think about it, what's going on. Suppose, if I go back to the end, we're dealing with the face of Lincoln as our data matrix. If we go over here, this represents what the most significant vectors are of the face of Lincoln as we go from the one with the most significant vector to the 50th vector. Note that, again, the original Lincoln picture was 512 by 512. If you want to reconstruct the Lincoln picture perfectly, you need a matrix that is 512 by 512. Here, what we're showing are, this is the U matrix and this is the V matrix. This is showing you a picture of the most significant singular vectors, okay, in the decomposition. Look at that matrix a little bit. And what do you see as you move to the right of this, from the most significant vector to the, let's say 50th most significant vector? Does anything, do you see anything as you move to the right?
Higher frequencies.
Higher frequencies, or by higher frequencies, more values jumping around. Does everybody kind of see that? So one way to think about what's happening when you do this thing, the earlier vector pairs are kind of rough cutting the matrix. Again, if you think about it, if we're doing the dot, the outer product of this vector by the transpose of this vector, I would expect to get a very blocky thing, okay? And when I sum in more and more, adding more and more of these things is going to give me more and more detail. Detail, of course, gets progressively less important. Here on the right is a graph showing what is the error. I had some measure of the error between the original picture and what I reconstructed after I had inverted the decomposition from the first k vectors. You will see that the error decreases rapidly with the number of vectors to a point. And then adding a lot more vectors doesn't do so much to reduce error, okay? So we end up with a situation where a small number of vectors is sufficient to give us a pretty good approximation of what we are, the original data matrix, okay? And so this is going to give us a way to take, let's say, an n by m feature vector, reduce it to an n by k feature vector, such that these k values, okay, encode a lot of what the original matrix actually looked like. Here is what happened when I tried to reconstruct Lincoln's face. If I used only 5, this summed up the first 5 matrices by the first 5, okay, pairs of singular vectors, okay? I got this version of Lincoln, which was recognizable. This is what I got after I summed up the first 50 of them. Okay. And here it is, it is quite sharp. This is showing me the error matrix. So I am missing, the places where I am probably making the most mistakes is where there is a lot of detail. Okay. But it should be clear that by taking the original matrix, taking only the important singular values, okay, this would kind of give me a feature reduction in the matrix, okay? And this can be useful for many reasons. One is by reducing the dimensionality of your feature vector, you need fewer values to train, okay? Fewer dimensions, you need fewer values, okay? It can be more robust. A lot of what you threw out, if this is what is there after you've thrown out 90% of your matrix, the other 90% of your matrix probably wasn't that important, okay? It may have even been noise on it. If there was, this is an old picture, if there was random dirt on the matrix, okay? This is the stuff that presumably is sitting in the less important, okay, singular values, okay, for dealing with it. So does everybody see that the value of singular valued decomposition is that it gives us a way to reduce the dimensionality of a matrix, okay, so that we get a smaller, more robust matrix that is often better for features. Any questions about that?
So since the higher singular values are cutting out noise, is it fair to think about it as like a set of frequency filters that we're applying?
I think that's a fair thing to do. So again, a similar phenomenon, when I think about here frequency filters, I hear of things like FFTs, okay, that when you did in processing signals, the Fourier transform kind of represents it as a, as the original signal as the sum of different waveforms, some of which are more important than others, some of which are less important. And a common thing to do is to say, well, let's delete all the high frequency waveforms because a lot of that is noise, a lot of that is less important. And so I think that it's a similar line of reasoning when we're dealing with with SVD. Okay, again, as in that kind of signal processing, a small number of the most important coefficients in a Fourier transform describe the signal quite well. It's the same kind of a thing that we're dealing with here. Okay.
In this case, eigenvalue decomposition is different from singular value decomposition, right?
Eigenvalue decomposition is different than singular value decomposition. One of the reasons is that the eigenvalue decomposition only works for a symmetric matrix. Okay, so the reason you don't tend to hear as much in the data, in the data science world of the eigenvalue decomposition, it is assuming your feature value matrix is is symmetric. And that's sometimes true, I guess, if you had like a graph or a network or something like that, an undirected graph. But generally speaking, feature vectors are often are usually not symmetric. Okay, and they're not always square. This sort of assumes that you've got an n by n feature vector, and that's not always the case. Singular value decomposition, on the other hand, will work with an arbitrary n by m matrix, okay, and yield dimension reductions, okay, that are powerful. Any questions about dimension reduction or matrices or any of this kind of stuff? Okay, good. So what I'd like to now do is shift gears a little bit, okay, into what you call into sort of machine learning methods. And I will still say the mother of all machine learning methods is linear regression. I trust you use that on your homework, okay? But we never really got to talk about it, okay? I'd like to now go into a little depth about how you build linear regression models. And let's start over here. So what is linear regression? We are often faced with a problem where we are given a collection of points of data values, okay, which I'm going to define as the x's, and we are given a value y that we want to try to predict. Okay, in an x-y pair, x is the, I guess the independent variable, and y is the target value. Okay, linear regression asks us, given the points, find the best possible line that goes through the points. Why is this a machine learning model or a model? Well, for any value of x, once you have the line, for any value of x, you can now predict what the associated value of y is, okay, by basically it being the point on that line. And so linear regression asks, given a set of points, find the line that best fits those points. Now, why are we going to deal with linear regression? Again, some people get nervous in today's machine learning world about why do you worry about a linear relationship? Because obviously there can be lots of different ways that the target can depend upon the variable. Linear regression is kind of, if we thought about when we talked about bias variance trade-offs, there's a high bias. We're sort of assuming that the model is linear. That our target is going to be value that can be expressed by basically the sum of coefficients times values. Why do we like linear relationships? The biggest one in my mind is that they are easy to understand. Okay, if I have if I know what my variables mean, and I have a linear regression model, by looking at the coefficient assigned to that variable, I can understand whether that variable is important to the model, okay, or not, okay? The other thing is that a lot of things grow, generally speaking, linear in other things, okay? The amount of money you get grows linearly with the amount of time you work. Housing prices grow sort of linearly, or at least increasingly with area. A bigger house is better than a smaller house. It may not mean that a house that is twice as big might not be twice as expensive, exactly. Maybe it's a little more, maybe it's a little bit less, okay? The weight that your weight is presumably grows linearly with how much food you eat, okay? Would be my presumption. So a lot of things are kind of naturally thought of as linear, okay, at least for understanding them. Now, most functions really aren't strictly linear, okay? Like I say, the housing prices, undoubtedly doubling the area of a house does not probably exactly double the price of the house, okay? But still, linear models are easy to understand, and there's good optimization procedures. And as we will see, there is a way to take linear regression and get rid of its dependent on all functions being linear in the variables, okay? And in general, we should be aware that if you really want a relationship to be linear, if you really want y to be linear in x, the best thing to do is just to measure it at 2 points, okay? If you measure it at 3 points, you'll probably learn it's not exactly a linear relation. Any questions about that? Oh, good. So one way that I think about linear regression, when you say, why is linear regression hard or different than solving systems of linear equations, I understand. What is solving a system of linear equations? It's basically saying I am given n lines, and I want to know what is the point that lies on all the lines. That is what solving a linear system is. Okay, and you did Gaussian elimination and things like that for that. In linear regression, okay, what we seek is a line that lies on all the points. Okay, and so there's two differences between linear regressions, finding the best fitting line and solving systems of equations. One is that we change the word lines to points. And the other is that we put a quote around the word all. Okay? When you're solving a system of linear equations, then in fact you want the point that lies on all of them. In regression, we are typically looking at trying to find a point that is kind of close to all a line that's close to all the points. Okay? It turns out that this is the major difference between solving linear systems and regression, because there is a duality transform that will convert points and lines. Again, we could think of remember I told you that you could think of an n by m matrix. You could think of it as n points, each of which are in m dimensions. You could alternately think of it as being a set of n equations, each of which is in m dimensions or has m variables. There is a duality transformation, which given a point st can be converted to a line where s is interpreted as the slope and the intercept is minus t. With this kind of transformation, you can convert any point, okay, st, to a line, okay, with two parameters, s and minus t. And that kind of, if you do this transformation, what used to be a point on all the lines in one space corresponds to a line through all the points, okay? So here, if we look at it, this is what happens when I take this system of two lines and 2 points on each line that are the blue points and the black points, and 1 point of intersection, which is red. If I do that duality transformation, the red point will become a red line. The blue line is going to become a blue point. The blue points are going to become blue lines, okay? The black line is going to become a black point. The black points are going to become black lines. And as you kind of see now, basically here, the red point was a line, okay, that went through what you call it. In this case, the red point was a line. What was a point that went through both lines. Now, okay, it has become a line that goes through the 2 points that represented the lines before. So if you understand this duality transformation, what used to be a point going through all the lines is now a line going through all the points. And so by that definition, if you wanted an exact regression where you weren't allowed any fuzziness, it's the same as solving a linear system. What makes regression harder is that it's a what you call it, an approximate notion of matching. We need a line that sort of goes through the points. Any questions about that? So what is the idea in regression? In linear regression, okay, when we have a line, we will say that the residual, okay, of a point against a line is going to be the error, okay? It's going to be y sub I minus the predicted value of y as a function of x and the parameters of the regression line, okay? So the error that we are going to have is going to be for all of our data points. We're going to compute what the residuals are, and the residuals are the distance here, and we are going to square it because the residual could be positive or it could be negative, okay? So what we're going to seek basically in least squares regression is a line that minimizes the sum of squares of the residuals at every point. And again, this is good because it means that a mistake high is the same as a mistake low. And it turns out that there is a nice closed form for this. Any questions? So how do we solve linear regression? Okay, the standard thing you learned in linear algebra was basically this kind of an equation, okay? Suppose we have our system, okay, where these are our points, okay? We want to take our data points and multiply them by a coefficient vector, okay? The coefficients are what's defining the line, so that we realize the target values, the y values, okay? The vector of coefficients that defines the best fitting line is being given by what you call it, by W, okay? And W is going to be, okay? This is, if we think about it, what is A transpose times A? Does anyone remember what that matrix is? Have we ever seen that form before?
Covariance of features.
That's a covariance matrix, right? And if we invert it, okay, basically what we're going to do is we're going to compute a covariance matrix. We're going to invert it and then multiply it by the transpose of the points vectors times the y values, okay? If we work out the dimensions of this, this will give us, if we have n points in m dimensions, okay, this will give us an m by 1, okay, set of coefficients, such that this is going to, W is going to be the coefficients to multiply the, each dimension of the x variable input, okay? Any questions about that? Now, what happens when you do a linear regression in one dimension? In one dimension, that means that our line is going to be of the form W0 plus W1x, okay? What is the best fitting line in one dimension? This has a closed form, okay? And it turns out that the slope of the line, that it depends upon x, is going to be reduced to the correlation coefficient of the x and y variables times the standard deviation of the y values times the divided by the standard deviations of the x variables, okay? So basically, if you think about it, depending upon how well the x and y values are correlated, that is going to shape the slope of the regression line. If let's say all the variables had been normalized to z-scores, the x's and the y's beforehand, the standard deviations would be 1. And then we would simply have the slope as being the correlation coefficient between them. As far as, so if we know what the slope is by this, one property of the regression line is that it will pass through the centroid of the x values, okay, and the centroid of the centroid of the points, which is going to be the mean of the x values and the mean of the y values. So if we know the slope and if we have a point on the line, then in fact, this gives us complete knowledge of regression in one dimension. Any question about that? The lessons here are, and if you think about it, this kind of makes sense, okay? If you have a bunch of points that are completely uncorrelated with x, if x had nothing to do with it, what would be the best fitting line as a function of x? If there was zero correlation, I guess you might as well just have a horizontal line, okay? If they're perfectly correlated, okay, then it's clear that the the slope of the line is going to depend upon how spread out the values of x and y are. That was what was captured by the standard deviation, okay? And again, if the if these were both normalized by z-scores, so that the standard deviation was 1, then in fact it was going to be exact, the slope, the correlation coefficient would exactly be the slope. Any questions about that? Now, where does this formula come from? Okay, and there's a property that the error vector, the residuals was the error vector. That was the original value y minus the prediction. The prediction, okay, given our coefficients, is going to be a times w. The error vector, okay, it turns out it must be orthogonal to the vector defining each variable, because if not, we could wiggle the the vector, okay, to reduce the error. So we end up in a world where basically these points times the residuals, the dot product of these things, has got to be 0. And by rearranging the terms and solving for it, that's where this kind of comes from. So if you believe this line about that the error vector must be orthogonal to the vector for each variable, this expression comes relatively simply. Any questions? Okay, what I'd like to do for the rest of class is talk about some tricks that you can use in building linear regression models to make them better, okay? And again, you guys should have some experience from this in the course of your homeworks, okay? You had to build linear regression models, okay? What I'm going to say is that the general issues are going to be about removing outliers, okay? Properly dealing with nonlinear, dealing with nonlinear functions appropriately, scaling and getting rid of correlated variables. So let's take a look at this. The first thing to note is that when you're building a linear regression, it's trying to minimize the sum of the residuals. If you have an outlier point, like over here, okay, it's going to want, the line is going to try to bend towards the outlier point, because an outlier is going to cause a large residual. And if you're trying to do a quadratic thing, you're doing the sum of squares, a large residual, when you square it, becomes an even larger square, okay? So one bad thing about linear regression is that it will go out of its way to chase points that are outliers, okay? If you deleted this outlier, there was a much better linear fit, okay, to the points. And so one way that you can get a better linear model is by reducing, by eliminating outliers, okay? When you guys had any of your linear regression things on the assignments, did you have any outlier points that you had to remove in order to get a decent fit? Okay. I don't know if anybody had any experiences with this kind of thing, but it should be clear that if you have points that are outliers because they are very, very strange beasts, they are things that are not like all the other things, okay? Removing them in a principled way makes sense, okay? If you, just find that you want to remove them in order to get a better least squared error, sometimes that's not a good thing to do. It's a question of whether they are outliers for a good reason or not, okay? Any questions? How would you identify which points in your point set were outliers? Okay. Can anybody think of how would we identify which of the endpoints is an outlier?
How many features are there?
Let's say this is in 200 dimensions, so you can't see it. How might you still be able to find which point is an outlier?
And you just determine the error for each point?
So one thing you could do is to fit the points like they are normal things, and then compute the residual for one point, for all the points. We would like to think that if you plotted the residuals, not the square of the residuals, you would probably get something like this. If you're getting some values out here, okay, these are probably the residual. These are the points that are least well fit by your linear model, okay? And so deleting those points, now you can identify these points. Deleting those points, okay, could dramatically shift the model because it has probably bent over fairly far trying to accommodate them. So that would be my way of identifying what the outliers are, even in high dimensions. Do a linear regression fit, see what points that have large residuals, and look at them very closely and decide whether they really should be trying to fit here or if something else is going on. Any questions about that?
If instead of using least squares, you just use least absolute values, could you mitigate the problem of outliers entirely?
Okay, so we will talk about regularization. Okay, so there's a couple of, let's think, we will talk about regularization a little bit later as a way to try to produce more robust kinds of things. But that actually is going to change the number of the weights of variables, the number of variables that get weighed.
Oh, no.
So what were you saying? That would not be doing what you want. What was your question again?
So the reason why the outliers move the line so much is because they're squared. You take the squared, you square the difference between that and the line to get the residual.
Right.
But
So
what if instead of squaring it, you just take the absolute value?
Okay, if you take if you do these kinds of things, that might be an alternate way to fit. Now note that the original formulation of least squared error kind of you don't have the same formulation anymore, and it's not as obvious to me how you fit such things. Okay, and in general, by the way, squaring things is actually telling you that you don't want points far from the line. Okay, you can sometimes, when you don't square these things, we'll talk a little bit about this when we get into nearest neighbor computations. We'll be talking about the different kinds of distance metrics. There's the L1 distance metric, the L2 distance metric, things like that. And there is the metric that kind of doesn't square these things. And sometimes you end up, when you don't square it, it means that a little error anywhere is equal. And that kind of sometimes doesn't really keep the line kind of as straight as you would, as anchored as you would like. So in general, squaring things is good. Okay, I don't think that's the problem. But outliers, I think, are bad. Okay, you're better off if you have an outlier that is a legitimately weird thing to get rid of it, I think, rather than to try to just reduce the penalty for the outlier. Okay, that's my view. Any other questions here? So getting rid of outliers is clearly a good thing. The other thing to realize is that although things are not always linear, we can incorporate nonlinear functions, okay, by making our data matrix more complicated. Suppose we have, as in a world like this, where let's say we have a set of points that look like this, okay, and we are given the values of x. Okay, if you look at this, this should look a little bit quadratic. I'm kind of hoping that that's going to be a quadratic thing. If we tried to do a linear fit, we would come up with something like that. How could we create a data matrix where we find a quadratic function? Note that if you have points of the form x, y, you could increase the dimensionality of your data set by adding both x and x squared as columns in the matrix, okay? And now, instead of having one coefficient you were trying to find, you're now trying to find two coefficients. How much does it depend on the x term, and how much of it does it depend on the y term, on the x squared term, okay? By adding other columns to our matrix with nonlinear functions of the original variables, a linear fit in this transformed matrix is going to correspond to a nonlinear function of the original number. Okay, does everybody kind of see what I'm doing here? If my original value matrix, let's just say I had the values 3, I only had one value, x, 3, 2 and 7. I'm going to produce a new matrix that has 3, 2, and 7, but also has 9, 4, and 49. Okay? And now, if I want to fit the quadratic, I'll just have the coefficient will be high on this column, but not on the linear column. So augmenting any matrix by, I will say, nonlinear functions of the underlying variables can be a good thing if you know what the dependence of it is. On any of on your last homework 3, was there any variable that had a nonlinear contribution to the target value? You were trying to predict grosses, I guess. Was there anything there that people noticed that had a nonlinear value there?
Yeah, a lot of the features were power law distributed. Even the gross was power law distributed.
Okay, so if there was a power law distributed, that's a little. If there was a power law thing, as we'll talk about later, maybe you would be interested in the log of the variable, adding x and the log of x. The square root of x is also sublinear. Okay, 1 over x is sublinear. Okay, x cubed is superlinear. You can augment, if you have a low dimensional data set, you can augment it by adding these nonlinear terms, and then the linear fit of these nonlinear terms is going to be a nonlinear model. Okay? Do people kind of understand this? This is an important thing to be able to do. Okay? Because this makes linear regression be able to do nonlinear things.
Professor, I have a question.
Yeah.
So why would you want to make linear regression do nonlinear things when, for example, as a power law, you could just make it a linear variable by taking the log of it and then upscaling your result?
Okay, you could if things are a power law. But
You-
let's say that I want to plot, let's say I want a model to predict what the area is. I want to know what the area is of a box that is X by X. Can I come up with a formula? I'm not very good at geometry here, okay? If I wanted to come up with a formula that is going to figure out what the area of a X by X square is, I may have some observed values. For 1, it was 1. For 2, it was 4. For 3, it was 6. Okay? This is not a power law thing. This is just a polynomial. This is a nonlinear relationship. It's a quadratic, right? If x squared is one of my variables, then I can fit it nicely. If x squared is not a variable, I can only fit it very, very crudely. Okay? And so it's not just a power law thing. It's a question of whether or not there is a nonlinear dependence on things. Okay? And often there is a nonlinear dependence upon things. Okay? For example, in New York City, okay, it would not shock me if apartments the price of an apartment grew quadratically with the size of the apartment, the area of the apartment. That having two 1,000-foot apartments is worth less than a 2,000-foot apartment. Okay? That's an example of a nonlinear dependency. And the claim is by adding extra terms, you can figure out how to resolve that. The good news is this gives you a way to add nonlinear functions. The bad news is, one, you have to be a little bit clever about which nonlinear functions to add. Okay? Because you can't add too many of them. Again, ideally, if you're fitting a model, if you have n points in d dimensions, okay, you want n to be much greater than d, so you get a robust fit. And the more, every time you add another value here, you're increasing the dimensions, okay? So you can't add these things arbitrarily, and you have to use your brain to decide what to add. But if you do this in a sensible way, you can now build a good nonlinear model of these things. Any questions about that? Okay, this is a useful technique to know. One other problem that sometimes can be that happen with linear regression models. So I don't think I really want to overstate this. Suppose, let's say, we wanted to try to predict the average income of a country as a function of its population and of the percentage of people that went to college. It makes sense to me that bigger countries should probably, in principle, get richer. More people earning more money. In principle, a higher fraction of the people that went to college probably means a more educated population, means, so you could imagine trying to predict the gross national product as a function of the population and the literacy rate, or the percentage that went to college. But note that people at least in the United States, there's 300 million people. The percentage of people that went to college is a number between 0 and 1. Maybe it's 0.5. I mean, the fraction of people who went to college, maybe it's 0.5, maybe it's a little more, maybe it's a little less, okay? It should be clear that if you want a model to predict things that are a function of the fraction and a function of the population, if you're going to try to have both things be components of the model, you have to take the fraction and multiply it by a lot, or take the population and multiply it by a little, a very small number, in order to make these things comparable so they can contribute to the target variable, okay? And having a wide range of coefficients, okay, is unfortunate for a couple of reasons. One reason is because there are numerical computation issues, and if you have a wide enough range on these things, it'll cause trouble. The other has to do with interpretability. One thing that's good about a linear regression model is that the coefficient that we use to multiply a variable tells us something about how important that variable is to the target. Remember, it functions something like a correlation. But if the ranges of magnitudes of the variables are wildly different, it can't be interpreted in this way. So one thing that is good is if you have data that operates over a wide variety of scales, it can be good hygiene, okay, to basically convert the variables to z-scores. Now the mean of every variable is the same. Now the standard deviation is the same. The coefficients will tell you something about how important that variable really is in trying to predict the target. Any questions? In theory, again, doing a z-score is just a linear transformation. So there is going to be a linear regression model, okay, even if you didn't normalize your variables like this, okay? But in general, we are happier with coefficients that are not wildly different magnitudes. Any questions about that? Okay, good. The next thing, as was mentioned, we heard the word power law. If you are either one of your variables is power law distributed, but your target distribution is different, you are doomed to a problem. Let's say we would do a frequency distribution of how many years of education people have had in the United States. What do we think the fraction of people with X numbers of years of education look like? Okay, does anybody have a vision? I can say I get a PhD, I would have a 19 years of education. Someone who graduates high school has 12 years of education. What do we think the distribution of the frequency in the population is? How many people have X years of population, of education? What do we think that distribution should look like? Does anybody have a feeling?
Yeah, I think power law is probably fair, where it's a negative exponent.
No, a power law would mean that there was an exponential. So let's think what it amounts to. In a power law distribution, rare values, outliers become rare, but they keep happening. They're not unbelievably rare. Okay? What do we think the distribution is? I claim that in the United States, it is probably something where almost everybody graduates high school. Very few people get doctorates, which lasted 19 years. A couple of people may get 2 doctorates. These are people who are probably crazy. But nobody has 100 years of education in the United States. No one has 200 years of education, okay? it is not going to be a power law thing. It is probably going to be a vaguely bell-shaped thing, is my guess. Okay? On the other hand, it's clear that the amount of education you get depends upon income. It would be perfectly rational to build a model that says how much does education, how many the years of education you have depend upon what your income is, or the income of your parents. Okay? Now, the income or the wealth we saw was power law distributed, right? That meant that it was not a bell-shaped distribution. To try to predict something that is bell-shaped, here the number of years, on a feature where it is not bell-shaped, okay, is asking for trouble. It can't possibly find a good coefficient here to change the shape of the distribution. What would make sense is, and even if the income was sort of, kind of bell-shaped, okay, there's a bigger problem. Bill Gates's income is so impossibly higher than mine that if we want to think of how many kids there are, you can't have a coefficient with a big dependent upon income. If there is a big range here, okay, there's no sensible coefficient that would make sense. Now, on the other hand, if you took the log of the income, this then becomes a more meaningful thing. Again, as we've discussed before, my wealth is probably between absolute poverty and Bill Gates pretty much equally on a log scale. There are things that, if this was the log of income, okay, there's a possibility that it can lead to something like this. So recognize that the z-score transformation is just a linear transformation. Taking the z-scores of power law variables won't change the shape of the distribution. But taking a nonlinear function like a log would have the property of changing the transformation, the distribution, to a shape that might be better than that. Any questions? Do people see why it's important to sometimes change these the target variables? Okay. Any questions? Okay. And again, the same kind of notion. Again, if you have power law variables for features or for targets, hitting it with a sublinear function is often, it will produce a bell-shaped distribution, ideally. That's something that's probably expressing something bell-shaped as the sum of features that are bell-shaped. You have a hope of something being meaningful here. Any questions about that? And I guess this is basically what I had said earlier, that one of the reasons you want to take the z-scores of the variables is that, you kind of get coefficients down to smaller things, and that those are easier to understand. The final thing I'd like to say about improving linear regression models is there is a problem when you have highly correlated features. Okay? Suppose I have a matrix where I have among the features, the rows are people, and one column is their height in feet, and another was their height in meters. What do we know about the relationship between someone's height in feet and someone's height in meters?
They're perfectly correlated?
They are perfectly correlated. Why is it? My height in meters, I believe, is my height in feet divided by 3.1 ... Okay? So they're perfectly correlated. There's a linear scale thing. What is the problem now? If I want to try to predict what my y is, where two of my variables are highly correlated, or even perfectly correlated, or even very, very highly correlated. What kind of problems does that create? Okay. Well, one, there is some confusion. What if, let's say, my Y value, let's say the probability I win at jump ball at basketball, is a function of my height? Should it be a function of this variable, or should it be a function of that variable, or should it be a function of both? Okay, it's clear if I have two highly correlated variables, okay, if they're perfectly correlated, equally good models could be made by using this one or that one, or a linear combination of these two. Okay, and this seems like a bad thing. It's also a bad thing if we think about trying to trying to identify what the coefficients are using the formula for linear regression. Here I've got a covariance matrix that I am taking an inverse of. If I have two highly correlated variables, this matrix, this covariance matrix, is not going to be a full rank, and I can't invert it. Okay? So highly correlated variables cause at least two problems. One is that there are many, many models that are an infinite number of different models that kind of do the same thing. And two, it causes numerical problems if you try to optimize it. How can we get rid of highly correlated features? Ideally, if you have two perfectly correlated features, you'd like to drop one of them. How would we get rid of, in general, correlations between features? Okay. One possibility is by taking a look at the covariance matrix and seeing where, basically measuring the correlation between each of the features. And if the correlation is too high, you could maybe throw one out. That would be a crude way to do this. What would be a better way to get rid of highly correlated features? Well, we talked about these dimension reduction techniques like singular value decomposition. Singular value decomposition is going to basically eliminate, okay, highly correlated features, okay, are kind of both going to get absorbed, okay, into one singular value, okay, and so this is one of the reasons why we want to do dimension reduction. If I took a data matrix where you add very, very highly correlated features, to get rid of that correlation, to get rid of that redundancy, is why we do the matrix dimension reduction things like singular value decomposition. Any questions about that? When you were doing homework 3 or homework 2, did any of you see evidence of highly correlated variables in your models? Okay, a lot of your feature values are probably fairly highly correlated. Did any of you have examples of highly correlated features, and did they cause you any trouble?
In homework 3, I found that almost every feature was correlated pretty highly with budget, which did seem to offer little predictive power as opposed to just using budget.
Okay, so the question was basically, you're telling me budget was important, but budget is what buys things. Why does cast power depend upon the budget? Well, if I have a big budget, I can get big stars to work for me. If I have a budget of $1.50, I cannot get big stars to work for me, right? So yeah, so you would expect that a lot of things are correlated with budget. What would be the right way to deal with this? Well, one way was maybe just to use budget, but there still are subtleties there. Again, cast power. Sometimes you have a director who, is someone people like to work with, and maybe they got a better cast than just what they could pay for. So I could imagine that these things are not always perfectly correlated. If you did dimension reduction, if you did singular value decomposition, you would come up with a small number of dimensions that capture what is really present in the factors that are present in your matrix. And that's actually what is valuable. Any questions about that? Any questions about about dimension reduction or linear regression, or how we can do linear regression? Build better models that way. Okay, if not, thank you. I'm sorry I had a fire drill, and hopefully that won't happen again. And, I will see. Yes.
I have a question. If you use dimensionality reduction, does it usually change the accuracy of the linear model, or does it usually not change it? Like, in terms of numerical stability, it makes sense why you'd want it, because highly correlated features make singular matrices. But in
Right.
terms of the actual fit, assuming that you had no numerical issues and you could have infinite precision, does it make a difference?
Well, there's a question of whether the things that are not whether the things that are not the major let's think about the budget thing. We saw the claim was with the movies that there's a lot of things that are correlated with budget. Now, we don't want to kind of throw away things that are unimportant. On the other hand, what if you had a world where basically you had a bunch of columns that were highly correlated with budget, but they also had, the differences was that they had a small amount of random noise added to it. Okay? So imagine a world where you have 4 features, all of which are essentially the budget, with some kinds of random noises attached to it, added to it. Now, would you be able to make a better prediction from these 4 columns than you would from the original column, okay, of just budget? I'm going to claim you're going to make a worse prediction, because if your model is cluing on the random noise that is being added, that is a bad thing. That's going to be an overfitting thing. In that case, if what you're looking at is kind of random noise or something like that, the singular value decomposition will throw away the high frequency terms. That's going to be the noise. And you're going to end up with a better model. Okay? If the signal is important, okay, if there is other signal that's kind of correlated but different, like height and weight are correlated with each other, okay, fairly strongly correlated, but not completely deterministic. If I want to know about someone's health or life, knowing both height and weight seem like important features, okay? If you did a dimension reduction, presumably one of the dimensions would correspond to something like height, and the other dimension, which would be kind of like the residual to it, would be kind of reflecting overweightness, underweightness on some level, okay? So again, I would say doing the, I will say usually will end up with a better model if you're throwing noise away from your feature, okay? If, on the other hand, these little differences are really something very, very important, perhaps you will lose detail when you did the SVD, okay? But generally, I think there is an increase in robustness when you do that. Any other questions about this? Okay, the intuition of why the reduced features might be more robust, that I think is kind of important. On the other hand, if the differences were signal instead of random noise, then the SVD would be unfortunate. Okay.
Is dimensionality reduction subject to outliers?
Is dimensionality reduction subject to outliers? The answer would presumably be yes. Okay. So there's no, okay. So right now what the dimensionality reduction is going to try to do is to remove dimensions that are unimportant. It doesn't have any control of removing points that are unimportant. When we were talking about outlier removal, we were trying to remove points that were unimportant, okay, that were misleading. So I will claim that's orthogonal to the issue here of dimension reduction. On the other hand, once you had removed, what I do imagine is, if you have outliers, you're going to end up having it, you know, it's probably going to find, you know, more components that are probably meaningful, trying to fit that outlier. Okay. But, and when you removed it, perhaps you would get away with fewer components. Okay. But again, the outlier or rows, dimensionality reduction is removing columns. Okay. Any questions? Okay, if not, thanks for your attention, and I will see you. We will actually take up with other variants on how you can compute linear regression. That will be important for several different machine learning techniques, and that we're going to talk about next class. So thanks for your attention. I will see you guys then.